Welcome back, and in this series of videos we're going to be looking at the transition metals. The transition metals make up most of the D block elements in the middle of the periodic table. It's an important part of inorganic chemistry and comprises a large section of your paper 1. So you're going to need your notes, and we're going to start on page 1. So the D block is this block in the middle of the periodic table, and they are all metals. So from scandium to zinc, they are what we call D block metals. So we need first of all to remind ourselves of what we mean by metallic bonding. So metallic bonding, if you remember, is the electrostatic attraction between the cations and the sea of delocalized electrons. And when talking about the strength of metallic bonding, like when we talk about the strength of any bonding, we're talking about size and we're talking about charge. In this case, it is the size of the ions and the number of delocalized electrons. So the smaller the ions, and the more delocalized the electrons, or the more greater number of delocalized electrons, the stronger the metallic bonding will be. So magnesium has a higher melting point than sodium because magnesium ions are smaller and they delocalize more electrons, and therefore the electrostatic attraction is going to be stronger. And we can use these ideas again to explain why something like potassium melts at a very low temperature of 64 degrees Celsius. Potassium is a relatively large ion. It only delocalizes one electron, so the electrostatic attraction is quite weak. In the D block elements, both the D and the S electrons are used in bonding, so you can delocalize the D and the S electrons. Now, because you can do that, you've got very strong metallic bonds, and that explains the very high melting and boiling points of these transition or D block elements. Before we go any further, we do need to sort out the difference between a D block element and a transition metal. So D block elements are in the D block and they have their last electron in a D orbital. But simply because something is a D block element does not mean it's a transition element. A transition element or a transition metal is one that has one or more stable ions with an incompletely filled D orbitals. Now please be very careful with your definition here. You do need to make sure you've got this one word perfect. So it is orbitals, not orbital. So you just need to be careful on that one. So zinc is a D block element, but it's not a transition metal because the only stable ion that zinc forms is a zinc 2+ ion, and that has filled D orbitals, not incompletely filled D orbitals. So although it's a D block element, it's not a transition element. So we think back to our work on lower 6th on electron configurations of carbon and of potassium, we get 1s2, 2s2, 2p2 for carbon, and 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So far, so good. And the first 20 elements fill up in the same order. But when we come to the transition metals, things start to get a little bit more interesting because we're introducing the 3d orbitals. And this requires us to have a look at the energy and the order of filling. So you can see here the energy and the distance from the nucleus. And generally, the lower energy ones get filled first. We fill 1s, 2s, 2p, 3s, 3p. But then if you look, the 4s is of lower energy than the 3d. So the electrons go into the 4s first and then into the 3d, then back to the 4p and so on. When we come to empty them, they empty in the order of distance from the nucleus. And because the 4s is further away from the nucleus than the 3d, it gets emptied first. Also, the process of actually putting electrons into this 4s and 3d orbitals make them change places. So when we come to take them out, they leave the 4s orbitals first. So first in, first out. There is one complication to this, and this is chromium and copper. So if we look at copper, Cu, and I'm going to use the abbreviated notation of argon, and then I'm going to add on. So we get 4s1, 3d10. You would have expected it to be 4s2, 3d9, but by having a complete d orbital, that allows me to stabilise the atom, shields the nucleus more effectively. So that's slightly less energy and it's slightly more stable. And I can do that because the 4s and the 3d are so close in energy. Chromium, similar arguments. Argon, 4s1, 3d5. In this case, by having one electron in each of my d orbitals, again, it confers extra stability, and that means that it counteracts the energy required to promote that electron from the 4s into the 3d. So with those two in mind, we can figure out the electron configuration for all the other transition metals or D block elements. So starting with scandium, we have 3d1, 4s2, titanium, 3d2, 4s2, then 3d3, 4s2. Then we have chromium, which is 3d5, 4s1, and then manganese, 3d5, 4s2, and then we'll go on as normal, 3d6, 4s2, 3d7, 4s2, 3d8, 4s2, and the last two again, 3d10, 4s1, and again 3d10 this time, 4s2 for zinc. But do remember, zinc and scandium are not transition metals because they don't form stable ions with an incompletely filled d orbitals. In terms of the maximum oxidation state, it goes up to a maximum of 7 and then back down again. So the maximum oxidation state we can get for scandium is 3, titanium 4, 5, 6, 7, and then 6, 5, 4, 3, and 2. So if we think back to our work from electron structure and periodic table, you'll remember that there is a general upward trend in the first ionization energies across a period. The reason for this is that the proton number increases, your shielding, well, that stays roughly constant. You're removing the electron from the same principal quantum shell each time, and the atomic radii decreases as you go across a period. So putting all those things together, you will see that there's a general upward trend. So here are the transition metals from period 3 and from period 4. So these are my 3D and these are my 4D elements. You can see that they are all very, very similar. And the reason for this is because you're removing the electrons from the 4s in each of these cases. So you're removing the same electron. So as you increase your proton number as you go across, you're also increasing the number of inner shielding 3d electrons. So they're relatively similar, and this also helps to explain why the d block elements have quite similar properties. So if we compare something like calcium with vanadium, with calcium there is a big jump between the second and the third ionization energies. There is not an equivalent jump between the second and the third for vanadium. Because if you think what's happening in calcium, the first two electrons are coming from the 4s, but the next electron is coming from a 3p. Now that 3p subshell is closer to the nucleus, you've lost your outer shell electrons, it's less shielded, so it's much harder to remove. But the gap between the 4s and the 3d is much less, so there's much less of a jump between the two subshells. And this non-major jump, or there's no major jumps between the 4s and the 3d because they're very similar energy levels, and that explains why there is not that big jump between the second and the third ionization energy for vanadium, whereas there is for calcium. So, as we said before, we remove the electrons from the 4s first, slightly further away from the nucleus, and it's slightly easier to remove those electrons once something has electrons in it. So you have to remember first in, first out. They go into the 4s first, but they also come out of the 4s first. So we're going to have a look at vanadium. So vanadium is argon, and then it is 4s2 3d3. So when it becomes an ion, it's going to lose the 4s electrons first. So the vanadium 2 plus is just going to be 3d3 4s0, and then 3 would be 3d2 4s0, 3d1 4s0, and the highest oxidation state is 5, 3d0 4s0. So that's why the maximum oxidation state is 5, because it only has 5 electrons in its d and its s orbitals. So if we move on to look at the zinc 2 plus ion, again it loses the 4s electrons first, so you have 4s0, 3d10. Now it doesn't matter which way round you put these. Some people put 3d then 4s, or 4s then 3d. It really doesn't matter. But this is the electron configuration of a zinc 2 plus ion. So yes, we would expect it to be stable, because this is a very stable arrangement of electrons. You've got 2 electrons in each of your d orbitals, and that effectively screens the nucleus. So it makes it very stable. So it's a very stable ion. The other ion which is isoelectronic with the zinc 2 plus ion would be the copper 1 plus ion, and that electron configuration again is 4s0 3d10. But notice the copper 1 plus is not as stable as the zinc 2 plus because of the loss of 1 proton in the nucleus. So copper 1 plus is actually quite unstable. But copper is still considered to be a transition metal because it has a stable 2 plus ion. And that 2 plus ion has the electron construction of argon, and then 4s0 3d9. So this has an incomplete d orbitals. There is a gap in one of the d orbitals, and that's what makes it a transition metal. Scandium is the other side of the D block. It's the beginning of the D block, and it has the electron configuration, it only has 1 stable ion, which is 3 plus, and that is just isoelectronic with argon. In other words, it has no electrons in the d orbitals, and it has no electrons in the s orbital. Again, yes, it's stable. Why? Because it's isoelectronic with a noble gas. Iso with noble gas, with argon. And therefore it's going to be very stable. Neither zinc nor scandium are transition metals. They do not form ions with incomplete d orbitals, and therefore they are not transition metals. Copper and the rest of the transition metals are, but zinc and scandium on the ends are not.